In the southeast of England, in a country garden bursting with life, Charles Darwin paces. It's the summer of 1859, and the great gentleman scientist is surrounded by living things in all their glorious forms. Wildflowers crowd the path. Bees gently hum across multicoloured blooms. Overhead, a mighty oak tree casts a dappled shade, squirrels darting up and down the trunk. Mushrooms spring up in the cool damp shade at their base, and even deeper in their leaf litter, earthworms and maggots wriggle. In the distance, the lowing of cows and the cooing of wood pigeons adds to the symphony. Darwin revels in the life that surrounds him and ponders it just as he pondered the exotic animals he recorded and collected in his voyages to the tropics some 20 years earlier. It was during those years in the early 1830s, spent aboard the illustrious HMS Beagle on its 5-year mission to map the coasts of South America, that the young Darwin, a 20-something-year-old naturalist, devoted every waking hour to scientific analysis. Of fossils and all manner of diverse life he came into contact with. From giant land turtles to reptilians, colossal whales, and even a vast array of seemingly insignificant insects, many of which had never been studied before. Some life forms in the Galapagos Islands in particular, a previously largely unexplored hotbed for biodiversity, varied ever so slightly from one another, from island to island, hinting at a common ancestor at some time in the past. Now, 20 years after the publishing of his modestly successful account of his travels, and on the verge of releasing a newer, altogether more revolutionary work, one that would eclipse the first in both controversy and ultimately success, all this life, in all its variety of forms, he imagines belongs to a great tree. Like the oak that stretches out above him, grasping toward the afternoon sun. Living species are like the green buds and leaves at the tip of every branch. The branches themselves were once green shoots too, ancestor species of what came before, dead now, but a clear path to those we see today. Tracing the branches back, they merge to more primitive ancestors, the foundation of many species yet to come. Ultimately, all the branches come back to the trunk, the ancestral line born of the first sapling, the first seedling, the first acorn. Darwin sees all life that exists and has ever existed positioned on this vast tree of life. Each new species to arrive has its own unique innovations, allowing it to branch out on its own. Some will flourish, maybe even sprouting successors of their own. Others will wither and die. But all are built on the template of the branch that came before. And at the beginning, long before the trunk even began to grow, a single acorn, the very first ancestor. the very first template on which all living things are built. But where and when did that first ancestor live? And what form did it take? Darwin imagines an early Earth, rocky, devoid of life. But on its surface, a warm little pond has just the right chemistry, the building blocks of existence. It's here, he suspects, in these murky pools, that we could find our first ancestor. Humble beginnings for the breathtaking diversity that is to come. A primordial soup billions of years ago. But that was nearly 160 years ago, and much has been learnt since Darwin's day. Since Darwin, scientists have been reconstructing trees of life in ever more detail, using the characteristics of living and extinct creatures to map the pattern of branches and discover common ancestors, right back to the first. The last universal common ancestor, or LUCA for short, is the ultimate grandfather to everything that came later, to all of life on Earth. We now know that life falls into one of three domains. All animals, plants and fungi are eukaryotes, with complex structures inside their cells. Even some single-celled, microscopic creatures are eukaryotes too, like amoebas and algae, making do with just one complex cell. Everything else alive is single-celled, but that's not to say that they are less diverse. These single cells inhabit every conceivable surface, as long as there is water. They are adapted to thrive in conditions that no other life could withstand. There are single cells that can survive intense heat, cold, saltiness, and acidity. And the denizens of this hidden world can be classified as either bacteria or archaea, depending on their chemistry. Because eukaryotes are so much more complex than either bacteria or archaea, scientists place them higher up on the tree of life. They came later, while the two other domains are more primitive. So, LUCA was a single cell. That much is clear. It makes sense too for the earliest ancestor to be among the simplest life possible. But modern science goes further than that. By analysing the DNA of bacteria and archaea, we can build trees of life for these primitive domains too. Instead of looking for shared physical characteristics, researchers look for genes that are in common. In 2016, scientists published a list of 355 genes that were probably part of LUCA's DNA, which opens a window on how this first ancestor functioned and the kinds of conditions it could withstand. But the view through that window is surprising. LUCA's genes give it the capacity to metabolize hydrogen as a source of energy. They also give it the tools for surviving at extremely high temperatures. This LUCA is something unexpected, adapted not to Darwin's warm little pond, but to a much more hostile environment. Able to survive, in scorching, acidic waters. In February 1977, a century and a half after the Beagle made its fateful circumnavigation around the Earth, a new generation of scientists in a research vessel off the South American coast made a remarkable discovery. As part of their studies into volcanic activity around Darwin's beloved Galapagos Islands, they dropped cameras down to a depth of more than 2.5 kilometers. When the photos came back, they revealed something entirely unexpected. Instead of lava, hot water poured out of the Galapagos Rift. Towering underwater chimneys emitting plumes of it, darkened by minerals and metals, so it looked like smoke billowing from the sea floor. These scientists were the first to discover Earth's hydrothermal vents, affectionately nicknamed black smokers, bizarre structures that form as seawater penetrates cracks in the crust. Magma close to the surfaces superheats the water to almost 400 degrees Celsius, flash boiling it and spewing it back into the deep ocean like an underwater geyser. On its way, the hot water pulls minerals from the surrounding magma and rock, enriching it into iron, sulfur, hydrogen, ammonia. The minerals in the superheated water build up around the vent, creating alien chimneys in the ocean depths. But there was more. 2.5 kilometers down, no sunlight can penetrate. The darkness is intense, and the pressure is 250 times that at sea level. And yet, around these mysterious black smokers, life was found. Not a few cowering, crushed sea creatures, but vast and blossoming ecosystems. Clams the size of dinner plates, bristling clusters of tube worms, and alien, hairy yeti crabs all thriving in this curious, hostile microcosm. This entire vent ecosystem relies on another unseen component: single-celled bacteria and archaea, which have the unique ability to convert the chemical energy from the black smoker's complement of minerals into biologically available energy: food. Elsewhere on Earth, all food chains ultimately come back to the sun. Plants capture the sun's light energy and convert it into sugars, which then support complex food chains of herbivores and carnivores. But on the ocean floor, there is no sun, no light to provide that energy. The single-celled organisms that live here take hydrogen gas or iron sulfide and similar chemicals and use them to power their own metabolisms. The other animals eat them for energy or enslave them within their bodies to produce energy in return for safe harbor. In this way, an entire community is built, based on the abilities of these weird, single-celled organisms, completely unreliant on the sun. And it's these conditions that would have been ideal for LUCA, our last common ancestor with all other life. The genes that LUCA possessed would have allowed it to survive 400-degree waters, It would have given it all the means to extract energy from hydrogen. It would have given LUCA the survival skills for this unimaginably weird habitat. At some point in the deep and distant past, it's now thought that our earliest single-celled ancestors clung to vents like these. Our lineage may not have seen the sun for millions of years. But that's not quite the whole story. Although LUCA may have been equipped with the tools to survive and thrive on a hydrothermal vent, other clues point to an altogether different kind of beginning for life on Earth. Scientists who study the chemical reactions involved in life's metabolism believe that the ultraviolet light provided by the sun was necessary to get some of those reactions started. Deep beneath the ocean, there's no substitute for that kind of energy, so the earliest life forms must have proliferated when the sun still shone. Once more advanced metabolisms were up and running, life could do without the UV boost, but those earliest reactions were reliant on it. And since chemistry works better when things are concentrated in small volumes of liquid, perhaps Darwin's warm little pond wasn't so far from the true cradle of life after all. But how can these two lines of evidence be reconciled? One points to hellish heat, crushing pressure and acerbic chemistry. The other to sun-baked slime in a much more familiar setting. The key may lie in the LUCA's true identity. Our last universal common ancestor isn't necessarily the first life form that appeared on the Earth. It is merely the first one whose descendants survived over billions of years to diversify into all living things we see today. So life could indeed have started out in a warm pond, relying on the particular sun-soaked chemistry found there. Perhaps in those early years it had the chance to become well established, and so proliferated, spreading to other warm ponds and larger seas all over the Earth's surface. Everything was going well for global colonization until a catastrophe changed the course of our world forever. For hundreds of millions of years, fire rained from the skies. Thanks to the cosmic dance of giant planets far beyond Earth, asteroids were sent hurtling towards this fragile cradle of life. This bombardment would have vaporized surface water and injected heat and exotic chemicals into the ocean, wreaking havoc on the tentative first life. Only the hardiest variants that could survive this cataclysm remained, driven towards the places in the ocean that avoided the worst of the bombardment. The depths of the deepest oceans, despite darkness and oppressive pressures, became a refuge from the fire and fury on the surface. Here, at least, the water remained, the chemistry stayed the same, and hydrothermal vents became beacons for the single-celled survivors. They provided warmth and chemical energy that these struggling organisms needed to stay alive. Adapting to use hydrogen as a fuel instead of sunlight was the only way to ensure the future of their lineage. Meanwhile, the surface was sterilized. The first life that had gained foothold in warm little ponds on the surface was wiped out instantly. Destined to leave no descendants, its succession stamped out. This was potentially the first great extinction, leaving behind just one weird group of survivors cowering in the depths. How do we know that this extinction really happened? With so few rocks and no fossils from this early time, it's certainly hard to be sure about the sagas that gripped LUCA and its relations 4 billion years ago. But this is a tale that explains the clues that all living things carry in their cells to this day. And there's one final piece of the puzzle that seems to corroborate our story. The asteroid bombardment eventually tailed off as the solar system settled down, and remaining asteroids were swept up by the planets of the inner solar system. The sterile Earth finally cooled again by about 3.8 billion years ago. But something miraculous followed. Just 100 million years later, the rocks bear a record of life. The first fossils, physical structures and chemical signatures, are locked into rocks that are 3.7 billion years old. These are sophisticated single cells living and dying at the Earth's surface in little more than a geological blink of the eye after a sterilizing cataclysm. Scientists believe that life like this would have taken many hundreds of millions of years to come about, so there simply wasn't enough time for it to start afresh after the end of the bombardment. Instead, it must have survived the Earth's devastation somehow, hiding away, developing and evolving. As soon as things calmed down, they were primed, ready to burst forth and take over the world. So, hydrothermal vents were most likely the unexpected but essential refuge for our earliest ancestors during the first apocalypse. They were the warm little ponds of that terrible time. They were sanctuary for LUCA, a record of that time preserved deep in our collective genetic memory. Darwin was probably right in more ways than he could ever have expected. Next time, we'll discover the devastating but life-giving convulsions of the first plate tectonics and explore an alternative, altogether more alien explanation for the origins of life on Earth. You've been watching the entire history of the Earth. Don't forget to like and subscribe and let us know what you think in the comments. And we'll see you next week.